Okay, so let's say that we have an infinitely large plane with uniform surface density sigma. We know that the electric field is normal to the plane. So above the plane, it's pointing that way. Below the plane, it points that way. And we also know from Gauss's law that the electric field is sigma over 2 epsilon naught. In other words, it's constant everywhere. And it's there's an n hat representing that the field is normal. But we want to evaluate the curl of the electric field. So let's think of doing this explicitly. And so we need to put the electric field in some coordinates. So let's say that we write this in Cartesian coordinates. So let's say that that direction is the y direction. So if that's the y direction, then the electric field is sigma over 2 epsilon naught j hat for places where we are above the plane, in other words, y greater than 0. Let's say, well, let's also say that this is y equals 0, and doesn't matter what the other direction is, but and then we would have minus sigma over 2 epsilon naught j hat for y less than 0. And so now we have it in Cartesian coordinates, and we can evaluate the curl of the electric field. But we know that the curl of the electric field involves components like the derivative of the x component, which doesn't exist, it's just 0, but it's the derivative of the x component with respect to y. Then we have the derivative of the x component with respect to z. Then we have derivative of the y component with respect to x, derivative of the y component with respect to z, the derivative of the z component with respect to x, and the derivative of the z component with respect to y. And given that we only have an EY, and the EY is constant everywhere, it doesn't vary with respect to x or z, and so this must be equal to 0. So the curl of the electric field is equal to 0, and there's nothing funny going on at the boundary, unlike for the divergence of the field, where we have a jump, right? So the divergence is not 0 at y equals 0 because of this jump, but that jump in the charge density doesn't affect the curl of the electric field. So we have that the curl of the electric field is equal to 0, and we'll see that this is basically a result for all electric fields that are produced by some distribution of charge.